let me introduce myself. I am the sales guy responsible for energy and uh, higher education research sector. Okay. Today we also have here Pedro Mário, that is our solution architecture responsible for higher education research. Um, we have also with us Dr. Stan Posing, that is our worldwide strategy HPC application solutions for domains in Earth system modeling and computational fluid dynamics. I will record this meeting. Let me start. Okay, I'm recording right now. And we also have Dr. Raghu Kumar, that is our senior developer technology engineer working in HPC applications for weather and climate forecasts. His collaboration extends to United States, European, and Asia countries as well. So that said, I will hand over to Stan Poulsen. Stan, please.
Fernando, can you hear me then?
Okay. Yes, perfectly. Yep.
Very good. So I'll just take about 10 minutes and walk through some of the aspects of our program and how it works, how we collaborate with other organizations similar to that in Brazil. First, we focus on 3 application areas. You all are very familiar with these. I won't get into the detail, but we've got people that work on all these kinds of projects. And since atmosphere is usually the most important in these models, I've listed here some of the several collaborations we have with organizations around the world. Now, these are not the only GPU developments in the world. It's just the ones where NVIDIA makes investments. And you see here a list of the models, the organizations we work with, and this is a very important column here, the funding source. They all have funding for these models for GPU development, and they provide resources along with NVIDIA to make these projects become available for operational use, production use, etc. So very important that we have that kind of aspects to our collaboration. I'm going to talk about a few examples here, but I'm sure you recognize a lot of these organizations, and these comprise both organizations who develop global models along with some important regional models. I'm getting some background noise, Fernando. I'm going to mute someone.
Let me see here. Okay.
Okay. Now, as far as the support goes, the aspects of the collaboration, the project gets some definition by myself usually. Then we have people like, and by the way, I'm not a PhD, Fernando. I don't want that mistake to be made. I have deep respect for those who earn PhDs. I studied mechanical engineering. I got a bachelor's and a master's. But anyhow, we have people who work on numerical model optimization. That would be like Dr. Kumar, you're going to hear from shortly on impasse. People that can help with network communications optimization, someone like Gerardo, who you probably have known in the region there. Machine learning aspects, not leaning, that's a misprint there. I'll show you an example from an engineer, David Hall, at our company. He works on projects globally. And then you have, of course, your NVIDIA local relationships of business development solutions architect, like Fernando, et cetera. A few quick examples. ECMWF, who we work with closely through a partnership with Atos. Atos is also important in the Brazil region. I know there's a large HPC presence there. They've moved their next HPC to the Atos system, and we launched a Center of Excellence. And NVIDIA people, Mellanox people, et cetera, are members of this new Center of Excellence. These comprise both projects in HPC and AI. I'll give you just a couple of quick examples. In HPC, they run a spectral model, as you know, neither impasse or FE3 or spectral model, so I won't get into details, but we've worked on a project to help them get scaling on the Summit supercomputer at Oak Ridge out to, you can see almost 2,000 nodes. And this was looking at their spectral transform. and got some really nice speed ups on that in a project called Escape, which you can go to this link and get more details. And then we've got 3 AI projects going. I'd say they're one of the leading organizations in the world looking at combining machine learning with numerical models. We've got this one to work on hopefully an operational deployment of tropical cyclone detection. There's actually a joint project with NOAA, and David Hall, who I mentioned, is involved in this project. A second project, I'm going to detail, related to model bias correction. This will help improve their data assimilation. This is also something we hope will become operational. We've got 2 engineers involved, Thorsten Kurth and David Hall again, working directly with ECMWF scientists. And then I'm going to mention that we have 2 sites currently who have operational NWP. The first example I'm going to show is the site that runs a global model, MPAS. You'll hear about MPAS, won't get into details. But the weather company, who's part of IBM now, runs MPAS, updates a variable grid of 3 to 15 kilometers with hourly updates on, you can see the number there of V100 GPUs used for that system. And there's details I included here. You can go and read more about the actual deployment and hardware used, including storage, network, and so forth. And it also led to NCAR installing a large A100 partition at their site because of the work we've done with MPAS. And again, you're going to hear from Dr. Kumar on that. Our second operational site is actually running regional models. This is Meteos Swiss. This has been going on for years. I'm sure you've heard about this. And the PI on this, Dr. Oliver Fuhrer, you're going to hear from in about a week from now on his FV3 developments. Now, what happened is he moved from Meteos Swiss to the U.S. to work on the FV3 model, and we'll next explore some of the possibilities with that in the second session we're going to have in this series. But at Meteos Swiss, they're still running operational regional models. They started with Cosmo, have gone to some very high resolution, short range predictions you can see here because of GPUs. And they're next getting ready for ICON, LAM, a local area model of ICON. So we've got a project going where we're working on ICON and very large systems like Selene, Joules. You probably have seen details on some of these in the press, some of the conferences rather. And then recently we did a study working with ICON. You can see we have 5 different configurations here to see how it would perform in a ARM CPU environment versus the most powerful AMD that exists today, both connected with A100s. And we did both CPU and CPU plus GPU comparisons of that. And this led to CSCS, who provides the HPC for Meteos Swiss, announcing their next system called ALPS, which will be based on ARM. Grace is the name of the ARM CPU that we have, and the GPU configuration. So we're getting really excited about this coming in a little more than a year from now. Okay, I'm going to stop there, Fernando, and I can answer questions now, or we can hold all questions to the discussion. I'll leave that to you to decide.
Any questions so far?
I'll make sure I get these slides to you if you want to distribute.
I have a question, but I don't know if it's the wanted to do. What about for GPU? What about is there some study for using half precision for weather forecasting?
The question's on precision, numerical precision?
Yes.
For most weather, we're seeing single precision used, and for climate, I would say more double precision. I think, Raghu, you might get into some of the details on that, I would guess. But Roberto, I can say for operational NWP, we almost see exclusively single precision.
Okay.
And it's because of the hour turnaround time required usually for the prediction. So, and then we're also lately investigating mixed precision because we have different precision options available on the A100 GPU architecture. And we can get into some of those details later too. But I think Raghu will address some of that when he gives his talk. And Raghu, are you ready to display? Are you
Yes, Stan. Can you hear me, Stan?
Yes, very good. Thank you.
Yes.
Perfect. Yep, I'm ready to share the screen.
Okay, thank you. And Roberto had the question on precision. I guess you'll talk about that.
Yeah.
Okay.
Yeah, so for the MPAS, at least atmospheric perspective, the precision has always been single. They haven't actually requested a double precision, even in the production runs. We haven't actually seen the requirement to go to double precision, at least not up till 1 kilometer when the longitude and latitude get more than 6 decimal places. But we also have MPAS Ocean, which I'm not presenting today, but MPAS Ocean is double precision, and we've been able to get a good success with that as well. So.
Okay. Thank you.
Sure. Stan, sorry. We have a questions from Alvaro. Could you share this presentation with us?
Yes, I'll be happy to. There's nothing here that's not public, so I'll send that to you straight away, Fernando. You can distribute as you wish.
Okay.
And thanks for the question, Alvaro. So, okay. Great. So I can see.
Me too.
I can see your screen, Raghu. Okay, thanks.
I guess if you are speaking, you are on mute.
Oh yeah, you need to unmute.
Yeah.
Thank you. So thank you for providing the opportunity to speak on MPAS today. I wanted to present a little bit about the portability, scalability, and performance. We have been working on this model for a couple of years now, and I have tried to tailor this presentation in such a way that it has a little bit of introduction to MPAS. I didn't know the familiarity with MPAS. I also have a good amount of depth on how we managed to do the porting process and how the MPAS on GPUs works in the execution, and also a few slides on performance from different perspectives, from a production perspective and also from a science perspective. And feel free to interrupt me anywhere in between in case you have questions or if there's something that is not easily understood in the slides. So I want to go through the collaborators we have, which are currently the current collaborators that we have on the project. A brief introduction to MPAS, where I describe the algorithm, the software, hardware used to benchmark, how the structure of the MPAS looks like. And then I want to go into how we actually went on with the MPAS on GPUs, what were the original goals, how did we actually port the small and large volumes, and what the execution hierarchy looks like on an MPAS when it's running on GPUs, and then a few slides on the MPAS performance. So currently, our collaborators include NCAR, which is National Center for Atmospheric Research here in Boulder, Colorado. We also have the tie-up with the Weather Company, which is basically owned by IBM and IBM themselves. And we have an ongoing collaboration with University of Wyoming for the code maintenance. From NVIDIA's side, internally, the people who contribute and maintain this code, we have myself and then Pranay, who's another dev tech, and Carl Ponder, who's another dev tech, and then Brent Lieback, basically who is the compiler manager who supports the OpenACC side of it from the compiler end. For those of you who are not familiar with MPAS, here's a brief algorithmic description. I'm not an atmospheric science guy, but I kind of know some of the basic terms here. It's a compressible non-hydrostatic equation written in flux form, and you can see the structure of the grid here. It's a Voronoi mesh. This is a finite volume method on a staggered grid, and we have an explicit time stepping mechanism. It's a Rangekuta or Rungekuta, whichever way you pronounce. It's a time integration. It's a third order time integration scheme that's used internally. Now, coming to the software, we are currently using the MPAS 6.3. The latest version is MPAS 7.3. So we are just one version behind, and the expected release for the MPAS 7.3 on GPUs is September end, or September last week. The compiler we have used to benchmark is the PGI compiler 21.5 or the NVHPC compiler 21.5 with OpenMPI. We also had to benchmark this for the CPUs in order to draw a performance comparison. So this would be with the Intel 20.1 compiler. So there are two modes in which MPAS runs. I just wanted to familiarize everybody with it, but typically there's what you call as a dry dynamics test case. It doesn't actually allow you to have a full physics, but just have what you call as a dry only die-core mode, basically used for battle clinic storms. The common resolutions they run are 120 kilometer, 60 kilometer, or 30 kilometer resolutions. The number of vertical levels they use is 56. I have tried to capture some of those here, and the performance shown here for all the MPASs are basically one time step with and without radiation. But there is also what you call as a full MPAS run, but it has basically the physics and scalar transport in it. The physics modules are pretty standard inside MPAS. It has the TTK or NTTK, which is basically the convection, WSM6 microphysics, the gravity, wave drag, YSU boundary layer, Mono-Nabokov surface layer, NOVA land surface model, and then the RRTMG for radiation. So the one you have seen here with the highlighted green color is basically the modules that run on GPUs, and the blue colors basically run on the CPUs, with the exception that RRTMG is lagged, which basically means the radiation kind of synchronizes with the rest of the physics modules once every 15 minutes or 30 minutes, depending on what kind of a radiation interval. The radiation interval often, of course, depends on the kind of resolution you're running at. The coarser the resolution, the later the radiation can synchronize. The finer the resolution, the earlier the radiation synchronizes. All of this is basically single precision, and the benchmark that we have used for the hardware that we've used for benchmarking is Cheyenne supercomputer, which is NCAR's supercomputer, which has Broadwell nodes. Summit supercomputer, which has the Power 9 plus V100 combo and 6 V100s per node. TWC has its own cluster to do the production for weather. They're also Power 9 plus V100, but with 4 V100s per node. And then we have our own internal Sedin cluster, which is a AMD plus A100 combo with 8 A100s per node. That's basically the hardware that I'm going to be presenting as benchmarks here. Coming to the MPAS structure, some of you might already be familiar. MPAS can be divided broadly into two categories, physics and the die-core. The die-core itself has halo exchange, and internally the die-core also calls one small module of physics called as microphysics, which is the WSM6 in our case. The physics scheme involves whatever I mentioned before in the previous slide, the boundary layer, gravity wave drag, convection, and radiation. From a source line perspective, the die-core is about 12,000 lines in total, and then the physics is about 100,000 lines in total. The halo exchange that is often used, in reality, it's as big as 12,000 lines, but only about 2,500 lines are actually used to do the communication itself. But from an execution perspective, die-core and physics take about 50% roughly, depending on the configuration. So this was how we started, or this is how the execution time is on a CPU when we started. Basically, it's an even split between the die-core and physics. Now, when we started the project for MPAS on GPUs, the goals were they wanted to achieve portability across all architectures. So basically, Xeon was there at that point of time. Xeon Phi was also there. And then we had our GPUs. The core goal was we should not compromise any CPU performance because MPAS had a wide base of users that were basically running or dominantly running this on CPUs. The second most specific goal was to avoid having if-defs because that would basically give a non-maintainable code as far as NCAR was concerned. They didn't want to have a code base where we had a number of if-defs. So it was basically avoid these if-defs altogether. The third part of it was to manage the porting and optimization costs. So basically, they wanted a single source code that would run on multiple architectures and no less than a 10% additional lines to maintain this particular portability. So that basically means we only had one option here, which was OpenACC at that point. We had to use OpenACC language to maintain the GPU and CPU portability. And then the expectation was to keep it under 10% of additional line count just to make it work on the GPUs. And the last optional goal was to basically, if possible, use all the hardware. So it should not be a completely GPU-based where the CPUs are idle. So it was basically a full node utilization kind of a concept. Now, coming to the porting process itself, you can see here there are three snippets of code. One on the top left here, and then the center right, and then the bottom left. So this is how the original code would look like. And this was basically the die core. We started with the die core because obviously it was 12,000 lines with 50% of the execution time, performance critical code, and small zone. So we took the code and moved from the part 1 to the part 2 here, where you can see here there are data directives in order to copy the data in, and then basic kernel directives. So here the kernel directives are used so that the compiler does most of the work on optimizing the loop inside. And at the end of the data is copied back. So this is basically a quick way to get it to work on the GPUs, but also the most horrible performance because the data copy here adds a huge performance overhead. And then, the kernel doesn't optimize. The kernel directive doesn't optimize as much as a user-defined optimization would be. So from here, once we get everything to work on the GPU, then we move towards this third part here, which is basically optimization. Now, before you can see here, the data copies are basically transformed into data present directives, and then the kernel directives are basically transformed into user-defined directives for optimization. So when we reach this phase, the assumption is that we would have basically optimized the data layer high above. When the application boots, we have a routine where every variable that's basically created is automatically created on the GPU. Now, since the die core completely works on the GPU, there is really no necessary for us to do any kind of data transfer between the device and the host. So it basically remains on the GPU forever. So we just acknowledge or assert that the data is already present and then move over, continue with the GPU execution here. So this is basically the layout of how we port a die core. Small volume, performance critical code. Coming to the physics, we are basically dealing with a huge volume here, approximately about 35 to 40,000 lines for a given configuration is the amount of or the volume of code that you need to port. And this becomes very tricky because you have a large volume, bugs can creep in very easily, and you also need to be able to isolate the bugs. And then in between, there's also version control, MPAS gets upgraded. So, there are some modules that do change, some modules that don't change. So this was mostly a difficult task. So we had to get more organized in this. So the way we did that was here. So you start any routine or any module with a valid marker to mark where you have put the if-defs here. Note that these if-defs are only for development. Once you have completed the porting, all of these if-defs go away. They're not actually in the production run. The if-defs are basically there to facilitate volume porting. So here you basically say if-def GPU debug WSM6. So this is taken from WSM6. So what this means is if you're debugging the WSM6, then only use this directive. So here, if you're debugging it, what we do is we basically run this on the CPU. So it automatically switches to an update host, and then none of these parallel loop directives are executed. So the whole thing basically runs on the CPU and then comes back. So if this is basically kind of a debug mode where we are trying to do some kind of an analysis. But if it's not a debug mode, then basically you're going into the GPU, and then executing these loops on the GPU. So this kind of allows you to turn on, turn off certain modules and see where the bug is coming from or originating from or how it's flowing. and then maybe allow you to track down and narrow the bug easily. Combine this with tools like kernel generator, KGen, or PCAST. It's much easier and much faster for you to narrow down and then track the bug down and then say, okay, this is where the bug is coming from. But other than that, yeah, the whole process of, again, going from basic code to kernel directives, data copies, and then coming to data present and then parallel loop directives is the way to go here as well. So once the debugging is done and everything seems to be validating, then you grep for this markers and then go ahead and remove all of these if-defs, or basically layer them as commits on the repository, such that if you don't want that if-defs to be there, then basically undo the commit, and then it would go back to looking like the original after you fix the bug. But that's the overall layout on how we dealt with porting a huge volume of code. Now, coming to how we did on an iteration, like a module by module basis. So basically, we have a baseline saying this is how the routine is going to look like. We fixed the software, we fixed the software version, architecture, and what's the configuration going to look like, what's the accuracy expected out of these variables here. Once we have that, then we use KGen. KGen is a Fortran kernel generator. What it does is it's an NCAR's public tool. It takes a huge volume of code, and let's say you just wanted to extract 500 lines of code. It will basically cut those 500 lines of code, add input and add output to it, and make it as a standalone application. So instead of building the whole application, you could basically just work with a 500-line kernel or 2,000-line kernel, depending on how you want to work. So this basically allows you to cut out the kernel and then make it a standalone executable. So we cut the kernel out, put the OpenACC directives, and then port the whole thing. So this is where the second snippet of the code you saw, we have data copy and then kernel directives. And then coming to the optimization process, we still have the KGen, but we're basically trying to move the data into data present mode and then putting in the user-defined directives. We profile, analyze, and then try to optimize the code. Now, once we have optimized the code, we move to the portability check, where we basically test the code. Now, if the performance on the CPU has been severely compromised, that is more than 10% compromised, then we go back to either the porting process or the optimization process. So this involves basically a lot of code refactoring. So if at all there is a loop that you can optimize to perform really well on GPUs, but it's really badly performing on the CPUs, then we basically don't do it. So MPAS is not a 100% GPU optimized code. Rather, it's about 80% GPU optimized code. The 20% is left out in order to maintain the portability at this point. Now, once it passes the portability test, then we come back, integrate the code back into the main repository, try and benchmark it, try to verify the code's results. And as I said, it's important to make a layered commit. So for example, all the markers and the if-defs go on one separate commit, and then the actual code goes on a separate commit. So this way, in the future, a version change happens, or there is a small modification to that module, you turn back, or you take that pull request where you defined these directives to debug the code, apply it on your new code, and then continue to debug. This makes the version control significantly easier for MPAS. But this is the overall approach that we took in order to actually complete the full port of MPAS on GPUs. Now, how does the MPAS execution look like in terms of when we are executing on the GPUs? So this is where we begin the time step, and it immediately comes into, you can see CPUs and GPU. In CPU, we have a separate split. What you call as the integration ranks and what you call as the radiation ranks. Now, the radiation ranks are only responsible to run short wave and long wave radiation and synchronize once every 15 or 30 minutes, depending on what kind of a resolution you're running at. The integration ranks, on the other hand, come in, they offload all of the different things onto the GPUs and come back and then do diagnostics and then, end the time step and repeat the cycle over and over again. Now you can see that whether it is conversion of MPAS die-core to physics, surface layer, boundary layer, gravity wave rack, convection, die-core. MPS switching. MPS benefits here because sometimes when the CPU is trying to switch, the GPUs are idle. So we do get to benefit off of some of the MPS ranks. And as mentioned before, the land surface model continues to be on the CPU. So you can see here, after the surface layer is done, data is transferred to the CPU. It does the land surface model, and data is transferred back to the GPU before the boundary layer begins. And I've also listed all the different routines that happens inside the die core. I'm not sure if people were familiar or not, but you can take a look at the different key components inside the die core that's being executed inside MPAS. But this is how the overall execution looks like for MPAS on GPUs. Now, moving on to the next slide. MPAS execution, how does it look from a hierarchy perspective or from a node perspective? Now, you can see here, the blue ranks here are basically MPI ranks that are dedicated to work on the GPU. So if I can go back to the previous slide, these offloads here are the integration ranks, what we call them. That's basically what you see here as the blue ones. The red ones are basically the ones that are doing short wave and long wave radiation. And the GPUs constantly interact with the blue cores here on the node. Now we do have a dedicated rank that is exclusively responsible for doing asynchronous I/O, and we also have per node a few cores dedicated to do the OS and maintenance. So this is particularly helpful on nodes like Summit, where we have a constant OS or some kind of a maintenance patches being done. So this is overall how the node is basically segmented to do the different parts of MPAS. Now, I know that I haven't spoken about Halo Exchange, so basically I thought I'll put at least a line on it. So one of the things that MPAS is notorious for is having too many Halo Exchanges. For a standard configuration, you have 136 MPI send and receives in a single time step, so you can easily see how MPAS becomes a communication-bound application. So we have rewritten Halo Exchange so far a couple of times, but we're waiting a new release where we have a more optimized Halo Exchange coming in at the end of September. And that would basically be, I think, the best Halo Exchange for GPUs and CPUs, and would probably remain for quite some time. But yeah, most of the bookkeeping, for those who are curious, we do not use CPU as the intermediate source to do the MPI. All of the GPU communications between the GPUs happen from GPU to the other GPUs directly. There is no CPU interference here. All the bookkeeping, or at least most of the bookkeeping, is done on the GPU itself. There is really no requirement for CPU to be involved in the Halo Exchange process. Now, coming to the performance, this is the production side performance on how we are running it at the weather company. And all of this is public information. There's nothing proprietary here. Currently, the weather company runs two different forecasts. One is a 15-hour forecast, and the other one is a 72-hour forecast. The 15-hour forecast is basically a hybrid mesh. It's 15 kilometer and 3 kilometer. 30% of the globe, basically all of the land, is at 3 kilometers, and the rest of the globe, which is ocean, is at 15 kilometer, giving a total of 24.29 million grid points. It has 55 nodes in total, 220 voltage GPUs, basically. As I mentioned before, we have ability to exploit MPS here, so we do run 4 ranks per GPU. So that's a total of 880 GPU ranks, or what you call as 880 integration ranks, and about 1,320 radiation ranks in total on 555 nodes. Now the time step increment is 20 seconds, and in order to do the 15-hour forecast, it takes about 52 minutes. And this is basically including the initialization, where you read the data from the init.nc file or the netcdf file, run the diagnostics, write back the file I/O. This is inclusive of all of those times. Coming to the other forecast, which is a 15 kilometer and 4 kilometer hybrid. Here, the 72-hour forecast is 15% of the globe at 4 kilometers, and the remaining 85% of the globe at 15 kilometer. The 15% is basically covering North America, Asia, and Europe. which is where most of the forecast is relayed to. So you have 4.7 billion grid points, 6 times lesser than, or 5 times lesser than the previous mesh. They run only this on 10 nodes, which is only 40 voltas. Again, 4 ranks per GPU, but significantly lesser radiation ranks here. The time step interval is 25 seconds, so each time step advances the model by 25 seconds. The execution time here is about 11,653 seconds, less than 6 hours. So it also, again, includes initialization, diagnostics, and I/O. So their target was to basically do this 4 times a day, and their target to do the 15-hour forecast was basically 24 times a day. So they wanted it to be under 1 hour for a 15-hour forecast, and under 6 hours for 72-hour forecast. Yeah.
I think that we have a question from Pedro Peixoto about the slide on MPAS performance, TWS production. Are those execution times per time step or for the full run?
No, this is for the full run. Sorry, I should have. I think I confused by saying that the plots on the next slides are for time step. This is basically total execution time. This is for doing the full 15-hour forecasts. And when I post these slides, I'll make that correction so that it's more clear about this. Yes. So this is for the full 15-hour forecast and the full 72-hour forecast.
And you're including I/O.
This is including I/O, initialization, and diagnostics, yes.
And does the I/O have a parallel file system? Would you know?
Sorry? I couldn't hear you, Stan.
Is the I/O substantial? I mean, does it have a parallel file system?
There is a little overhead, but it's still, at this point, a little bit of asynchronicity. It is hidden. It is hidden, but there is still a small overhead, yes.
Okay, thank you.
Perfect. Yeah, I will fix the slides when I post it, and make sure that there's no confusion about this. Yes.
Dr. Freitas has his hand up.
Yep.
Oh, yeah. Can you go back to previous slides, please? So for the 15 kilometers and 4 kilometer hybrid mesh, do you mean that you need basically 3 hours to produce 3 days forecast, right?
Yes, that is correct. It's about 3.5 hours, but yes, you're right.
Okay. So why you use it so short time step for? I suppose that you have to use the same time step for 15 and 4 kilometer grid resolution, right?
Yes. This is not our choice. This was their choice, the weather production, the weather company's production choice. Just because they could do it, they just did it. There is no real necessity for you to have such a lower time step. That is correct.
Okay. Do you have any idea about, for example, if you have a 10-kilometer resolution but global or uniform resolution, not hybrid mesh?
Yes.
How this time would change?
Yes. I can actually show you. I think once I finish this, I can actually pull up some more data for you. We do have 10-kilometer, 5-kilometer separate benchmarks. And you can actually get the correct feel of how this would look like. So yeah. I can probably even add that slide in the final presentation. But yes, I can do that.
Okay. All right. Thank you.
Yeah.
Yes. We have another question on chat from Álvaro Fazenda. What is the strategy in I/O? It makes inputs in advance, and is your how to say this? Stan, could you help me? Output asynchronous output.
Yeah, asynchronous. Yep.
Okay.
Can you see the chat, Raghu? Or?
Oh, I can't actually. I don't know how to enable or.
Okay. What is the strategy in I/O? It makes inputs in advance and asynchronous outputs.
No, it's not that advanced actually. Basically, what we do is, in the beginning, when you're reading the initial condition file, every rank contributes a little. So, including the 4 ranks per GPU that's there, they contribute a little bit in order to boost that initial reading file. But when it comes to write back, that's where the synchronicity comes from. When you have a variable that's ready to be written out, you just pass it on to a different rank, and then the rank is responsible in order to write that back. And that happens when the impasse is executing. So the asynchronous is still being developing phase. I wouldn't say it's that advanced where everything is completely asynchronous. In the beginning, it's more of a parallelism because none of the GPU ranks or the radiation ranks have any task till the file is loaded. So everybody contributes a little bit. But once the file is loaded, then they set aside a few ranks to dedicatedly to write back to the streams. So that's where the asynchronicity comes in from. So the write back is where you have asynchronous, but the read in is basically still parallel. Does that help answer your question?
Yes, thanks.
Yeah. Perfect. So coming back to impasse performance. Now, once we know how the production looks like, from a science perspective, how does this look like and how many days can we simulate in a year kind of stuff. So here, what we're comparing is between Cheyenne, which is a Broadwell node, fully subscribed, run with an Intel compiler and OpenMP enabled, versus Summit, which is basically 6 V100s per node. And then what the bracket indicates here is basically, here 2412 is basically 24 ranks to do the die core, 12 ranks to do the radiation, 18 ranks per node to do the die core, and 24 ranks per node to do the radiation. That's the kind of label, data label I presented there. What you can see here is basically that the blue line is where you can see the scaling curve. So you can do 1 day per hour and then climb up. But on the Summit with the Voltas, you see a 3x bump, and then you start from there. Now, there is a little bit of lagging here. That's because of the MPI issues I just mentioned. We have a halo exchanges that are about 136. So in the September release, you should see the fix where this doesn't come down, but actually is parallel to the Broadwell processor. So we have the potential here with V100 itself to scale all the way up to 1 year per day. That's the strong scaling curve for 10 kilometer. So for the previous question you were asking, so you can basically, I can provide you this plot, and then you can take the X and Y axis from here and then, do that. But I'll also try and provide you a separate table on how the forecast looks like. Now, coming to how does this performance compare between V100 and A100? So all the previous results you saw were from the Volta architecture. Now, at lower resolutions, when you're running, less points per GPU, it's about a 1.4x performance boost on the A100. But when you bump up the number to at least 80,000 or more points per GPU, then you can actually see the A100 basically here performing about 1.8x better than the Volta architecture. So just to get the feel right here, the y-axis is time per time step, so lower is better. So as such, you can see here the orange one, which is the A100, is performing significantly better. Now, what this also allows us is the V100 only had a 32 GB card, which was the best. But the A100 has, I hear some background noise. I'm not sure.
Agu?
Okay.
I think Álvaro has a question.
Oh, okay. So
okay.
The 30 kilometer is a new capability. So here we are able to run with 655,000 points per GPU because of the new 80 gigabyte cards that are available on the A100. So more RAM and more memory bandwidth allows you to basically run denser and denser points. So what this implies for science perspective is not only can you target faster performance on the GPU, but if you're just looking for a low budget runs, then the A100 can offer you that as well. So basically, you can go ahead.
We have a heads up from Álvaro. Álvaro, do you have a question, right?
Yep.
Okay, go ahead.
Okay. Are you using Tensor Core in this
No.
GPU performance?
No. So Tensor Cores is exclusively DL at this point, or at least we don't have a means to exploit the Tensor Core inside of NPAS. So these are all purely HPC. There's no use of Tensor Cores. Yeah.
Okay, thanks.
So yeah, on the one side, we have faster and faster performance on the GPUs. On the other side, now with the 80 GB card and the additional memory bandwidth added to the A100, you are able to run a significantly denser amount of points on fewer GPUs. So for example, with 30 kilometers, you're basically using just a single A100. So that basically means that 15 kilometers, you can just use 4 A100s and still be able to run it. So 10 kilometers, you're basically able to do just 8 GPUs at this point. So that's basically one DGX machine to do a full 10-kilometer run. So the NVIDIA is trying to facilitate both faster performance as well as denser points, so lower maintenance cost. Coming back to the portability, so the original goal was basically to actually not lose any performance. You can see here, this is basically only the die core, the plot I have presented here for. What you see here is the blue color is base code, and then the red one is the OpenACC code. And anything less than 40,000 points per node is identical results. And anything above, whether it is single precision or whether it is double precision, we really don't see a performance difference between 1 to 4%. So that's why NPAS was basically accepted by NCAR. NPAS on GPUs was basically accepted by NCAR to be their code for now. Apart from this, I've also mentioned here, the weather company has verified that the OpenACC code in the production with full physics runs with less than 1% performance penalty. So if you run the base code and if you run the OpenACC code, the timing is almost identical. It's less than 1% difference between the two. So this is basically to show that we do have a portable performance code in the OpenACC NPAS. That's all I had for you guys, but I'll be happy to dig up additional data based on the questions. I wasn't sure what you guys were looking for, but I do have a number of other slides as well. So,
Raghu, I'd like to ask a couple of questions real quick. So I know Dr. Freitas and Alvaro, I think Dr. Freitas was the primary author on a GMD paper about Brahms. Brahms is their regional model.
Mm-hmm.
It uses physics like Thomson, aerosol-aware, RTMG, etc. Seems like we might have some GPU developments for physics also that you might just describe briefly.
Yes. So right now we are in the process of transitioning NPAS 6.3 to NPAS 7.3 on the GPUs. One of the benefits of doing that would be you would also get a regional NPAS, which is basically the WARF equivalent, where you can actually run a local mesh instead of a global resolution model. That's one of the benefits.
Sorry.
But the second part of it is...
Sorry, I must have misled here. So they're going to develop their regional model today, Brahms. They're going to develop a global model. They're going to migrate Brahms physics. The Brahms physics will be migrated to the global model.
Got it. Okay, sorry, my bad.
That's fine. And I was just mentioning that they might be able to take advantage of some regional physics that are already existing. Okay, thanks.
That is correct, yes. So we have what you call as a unified physics repository that is basically a common repository for regional models and global models. And what we are trying to do at this point is basically port all of those physics onto the GPUs. Thomson is basically aligned to be ported onto the GPUs by the end of this year, and it's also a target requirement for the weather company at this point. So you would see a majority of these models that you probably are already using to be ported on the GPUs as well. So if you switch over to the global model, that will probably come in as free of cost. Yeah.
And then as they adapt their physics, we could perhaps help with some OpenACC developments we have in existing GPU-based physics.
Yes, I think, yes. We are basically looking for means to port, and if there is a use case from them, that would basically motivate us to actually port the remaining portions of the physics, yes.
Okay, I'll stop so they can ask questions. Thanks.
Uh, let me say a few words about the project that we are running in Brazil now. So we are planning to develop a newer system for Brazil, for the operational centers, and we are in place to try to understand and decide which the dynamic core is the best for our purpose. So we are starting to think about adopting MPAS or adopting FV3, right? We have some expertise in Brazil in terms of the physical parameterizations that we have developed for BRAMs. As Dan said, we have also the global model, CPTEC global model that has a full package of the physics parameterization. And our plan is to bring our expertise, our parameterization that we have used for a long time, to bring in the MPAS or FV3, depending on what you are going to decide, which dynamic core you are going to use for the next generation of the Earth system brought in Brazil. So one question that I think will be important that what's the degree of work has to be done to convert one microfuse package, for example, Thomson, the Thomson 2014 from WRF worth. How you can give us idea how much work has to be done to convert some microfuse package that was primarily done for CPUs to be applied on GPUs with better performance.
So luckily for the Micro Thompson, we recently reviewed it because the weather company also is beginning to think the Micro Thompson is one of the better microphysics at this point. We assessed it, and it's actually not in a bad shape. I want to split the time to actually port and optimize into two phases. The phase one is where we, as DevTechs, personally port and optimize the code. And this shouldn't be more than anywhere between 4 to 6 weeks. That's basically the maximum amount of time you would take in order to port it. But second phase is where you want to commit this code and make it public and then accessible to everybody, and that takes time. That's depends upon the NCAR because they are the repository owners. So if we have enough pressure, for example, if you have companies like PwC and yourself, for example, insisting that the microphysics has to be done faster, then we can pressure them to actually getting an approval in 2 to 3 weeks. So we're talking about a couple of months of work in order to port. It's not a significant effort, and we plan to do that anyway this year because, as I mentioned before, by December, we really need to have microphysics, the Thomson basically ported onto the GPUs for other production purposes, yes. So by the time you make a decision, most likely it would already be done, but yeah.
Okay, right, thank you.
Sorry.
Okay.
Well, I believe their Thomson scheme was the aerosol aware. Is that the one for MPAS also?
Yes, that's right, yeah.
Yes, that is correct. It's actually taken from WARF, and it is one of the options that, apart from WSM6, it's identical, yes.
Yeah, it's the same that we use in VRAM. So.
And
yeah,
would there be a match with the current version of WARF? WARF is at 4.2 currently. Do you update VRAMs with the updates with WARF?
No, we actually have our own parameterization. We share some parameterization with WARF. So, but you have several kinds of parameterization that originally come from RAM's model that was developed by Colorado State University a long time ago.
Oh, okay.
And but you have all developments done in Brazil.
Thank you.
Right.
Raghu, we have another question from Dennis. How different is the performance between MPAS grid and regular grid?
So I'm not sure how to interpret the difference between MPAS grid and regular grid. So does that mean
maybe Cartesian?
What are the two grids?
Cartesian?
I think it's the same question I have is, for example, if you have a 10-kilometer uniform resolution MPAS, how this change, for example, if you have 15 and 4 kilometers. Think about to have 4 kilometers over South America and 15 outside, and compare with a 10 kilometer globally, for example, how will be the change? Because I think the time step, you play a lot of role on accelerating the code here, right?
That is correct. The time step here is basically determined by the finest resolution that you have. So if you have a hybrid between 15 and 3, we go with a 3 kilometer time step. And if you have a uniform 10 kilometer, I think 10 kilometer, if I remember correctly, is
about 51 minute, right?
60 seconds, I think. Yeah, that's what we run it at 60 seconds, but yes, somewhere close by to that number. So yeah, so you would have a significant difference in the time step, but the time per time step, as far as the hybrid grid or regular grid is concerned, remains unchanged. We don't see any performance discrepancy between having a uniform grid versus a hybrid grid. We have tried to benchmark this in several different ways, and we haven't come across a performance discrepancy there. But yes,
Alvaro,
yeah.
Alvaro has a bunch of questions for you, Agu.
Okay. The first one is about the binary reproducibility. What the magnitude of the difference when you run the code on GPUs and CPUs? It's comparable if you just change an option in the compiler, for example. What can we expect about this kind of issue?
So let me see if I understood the question right. So if you take the OpenACC MPAS code, you are asking if what is the different procedure to run the CPU and different procedure to run the GPU?
What the difference in the results? Because you are running you are processing in different hardware.
Yes.
The numerical consistency.
These are all numerically consistent. These are all numerically consistent. So there are two kinds of tests that we run in order to validate MPAS on GPUs. One is more of a statistical validation. And the statistical validation is not open source. It's a proprietary code exclusive to TWC. We have passed the statistical validation in order to show that the GPU and the CPU results are basically one and the same thing. Now, coming to the other side of it, there is more open source validation, which is also supplied by NCAR at this point. And here it actually marks the differences all the way up to about 5 decimal places for variables that are considered important. And if it thinks that there is a possible failure in this particular data, it flags it out. And so far, the OpenACC code that's available publicly has had no issues. We have always passed validation there as well. So if you have a bunch of variables that you consider to be statistically important, we can, I can take the time to run it and then use the tool to see if we can successfully validate the code for you as well. That's not going to be a big issue. But the numerical consistency is pretty good between the GPUs and CPUs.
Okay, thanks.
In order to put it in a different perspective, so let's say you have a WARF or you have an MPAS running on a PGI CPU compiler. So if you are able to provide us with a data set where you have a set of results on the CPU compiled by the PGI compiler, then we can get you almost the same bit for bit on most of the data except 1 or 2 where we would probably have 5th or 4th decimal places on the GPU as well. So.
Okay, that's a good result. The second question is about the performance on multi-thread if you're using OpenACC, because you are trying to make a portable code between CPU and GPU. Okay, I think I don't know MPAS, but I think MPAS does not have the multi-thread version. They do not implement OpenMP, for example, in MPAS. So you try to run the same code, the same OpenACC code on a CPU, on a multi-thread CPU to check the performance. Could you talk about this issue, please?
That is correct. So OpenMP MPAS is there, but it's not very well optimized in physics. Yes, it is there, but it's not an optimal code for physics. We do see that the OpenMP is pretty high up. The parallelism is not sufficiently exposed in physics, so it often suffers from a small amount of performance deviation. The way NCAR or any other production company overcomes this is because they avoid the OpenMP threads altogether, and instead they spawn sufficient number of ranks to keep all the cores and hyperthreads involved inside the CPU. And that seems to be working well for them at this point. And that is the reason why there hasn't been a significant effort in order to optimize the OpenMP for MPAS. On the second side, the OpenACC actually provides you the same optimal performance that is coming with the MPI ranks. So our code is tested for both multi-threaded as well as GPU. The OpenACC works on CPU as well as GPU at this point, and it gives you both numerically correct answers. And this is all available for you to test. I don't think you need to cite any NDA or anything. It's currently publicly available for anybody to test it out too. So you can actually download the OpenACC code, and you can contact me if the instructions are not clear. So you can basically go ahead and change only one flag. Instead of saying OpenACC for GPU, you can just say multi-core, and it would still compile and run the data for you. So you can basically test it out yourself as well. I'll be happy to help you with any instructions you need there.
Okay, thanks. And are you trying to implement another version, for example, in OpenMP version 45, for example, because they have to support to GPU and accelerators, for example, but you don't have plans to do that?
No, we don't have any plans.
OpenACC will be used.
That is correct. We don't have plans to do OpenMP GPU port. I don't know if I speak for NVIDIA, but from my personal perspective, OpenMP does not provide enough flexibility for me to handle the GPUs in the most optimal manner. We are already, as I said before, we already lose 20% of the performance just to maintain the portability on CPU. So the OpenACC code itself is not fully optimized for the GPU, just to give room for the CPU to perform well. Now, if I lose that, if I combine that with the lack of flexibility in OpenMP for GPU optimization, I might lose a lot more. So that's why there is no motivation at this point to pursue that. Because
PGI compiler has support to OpenMP version 4 and higher.
That is correct, but due to the OpenMP standards, there is a restriction on how much of flexibility their user can have in order to optimize the GPU from an OpenMP perspective. That's a standard. That's an issue with the OpenMP standard, not with the compiler itself. So the OpenACC has a more flexible standard where the user gets to control a lot more parallelism on the GPUs. So that's why we prefer OpenACC over OpenMP. At least I prefer. So yeah.
And the last question, is about the load balancing. Mm-hmm. I don't know if MPAS suffer from this kind of thing, but did you have any experience with that using GPUs? Using GPUs for correct the load, if any possible load imbalancing?
That is correct. The MPAS does have a load imbalance issue. The load imbalance doesn't come from the CPU GPU, but rather than the radiation ranks. Now, you have a huge set of radiation ranks dedicated, right? So I think, for example, here I was talking about 1,320 radiation ranks. And as you know, the shortwave code, which is pretty significantly big and is also most time consuming, only works on one half of the Earth. So when there's night side, the sun does not fall in, so there's no shortwave. So those threads are completely idle, and there's a kind of a load imbalance there. So there's a sweet spot that you have to find by benchmarking repeatedly in order to eliminate the load imbalance. So for example, if you have a significantly less amount of dicore ranks or significantly high amount of radiation ranks, you often observe the impact of load imbalance, and it actually deteriorates the performance. But so far, we have been able to almost always find a space where we can reasonably find the sweet spot between radiation and the integration ranks to eliminate the load imbalance. However, a couple of more things I want to bring out is the land surface model. Having too many less ranks on the CPU for doing the GPU work basically means less amount of land surface. So let's assume, hypothetically speaking, we are dealing with 163,000 points per GPU. And if you're looking at like 6 GPUs or 8 GPUs, right, on a per node basis, that's 1 million points of NOVA land surface model that the CPU has to deal with. So that becomes a kind of a load imbalance there, because the CPU is now trying to sort out the land surface model with a very less amount of ranks. So obviously the solution here is to move the land surface, which is what the MPAS 7.3 release is going to do. You would have the land surface completely ported out, but there's nothing we could really do about the load imbalance between radiation and integration at this point. So for that's why we basically kind of kept that flexible to choose how many integration ranks and how many radiation ranks you want to set up. And that most of the time takes care of load imbalance.
Thank you very much.
My pleasure.
Raghu, there was a question on ensemble computing.
Yes,
when it comes to ensembles, considering each member is an instance of the model, are there improvements when running the code with GPUs? I don't believe so, but maybe you could comment, please.
No,
you can't use MIG or anything like that. You wouldn't share ensembles on a GPU.
No, we have been experimenting and seeing how well we can deal with it, but no, there's no quick solution. I think Stan and I have been working or following papers where the ensembles are basically kind of have a DL approach, where you run a base model and then try to predict the ensembles using the DL method that's significantly faster rather than actually running each ensemble. But other than that, no, there's no quick fix for the ensembles on this side.
Yeah, the summary would be each ensemble member would run independent of the other.
Yes.
On its own set of GPUs.
Yes.
Okay, thank you. That was from Carlos.
Okay. Any other questions so far?
I have a question.
Go ahead.
Can you say that the most of effort of porting the MPAS code was to porting the code before to implement the OpenCC directives?
So I kind of had an intermediate break. Can you repeat the question? Sorry.
Okay. Can we say that the most of effort of porting the MPAS code is before to make a refactoring the code to allow use the OpenCC?
Stan, were you able to hear the question? I have some noise on my side, so were you able to hear the question?
I'm sorry, I was typing to Yao had a question, but sorry, Roberto, once more, please.
In order to allow to use better use the OpenCC, can you say you have to most of effort is to refactoring the code, refactor the code?
Oh, so you're talking about, I think I got the question. You're asking how much code we had to refactor.
Yeah, how much can you get away with not refactoring, I guess, is the question.
Yes, so actually that's a very good question. There are significant portions of this code where we have not refactored at all, and we have gotten away with it. One of the key examples there is Mononabokov. The reason being, number one, the code was written in 1970s, so it actually follows the F77 syntax. So there are a lot of go to jump, which is like a tricky, very tricky execution style when it comes to GPUs because it's considered a branching statement. Surface layer also takes less than 1% of the total execution time. So we got away with actually not refactoring any of the code there. But when it comes to MPAS itself, fortunately for us, unlike other codes, MPAS was pretty well written, meaning to say the loops were always together, the parallelism was well exposed, the parallelism was inside the core kernels. it was a very well-written CPU code, and as such, we didn't have to refactor so much in order to gain the GPU performance. The fact here, or the honest truth here is, because it was a well-written code, we get away with basically dumping more points in the GPU and hence extracting or exploiting that parallelism on the GPUs, as opposed to very, very much focusing on the refactoring. Now, the other side of this is where we really, really had to refactor was Halo Exchange. The Halo Exchange was originally written with linked lists, and the linked lists are not something that's very good for GPUs because it often loses the address of the host pointer. So you kind of run around in circles, and there are exceptions all over the place. So we had to significantly rewrite Halo Exchange from a linked list perspective to an array so that we can get the pointers right. But those are the two extreme sides of the story. I don't know if I kind of gave you an overall feel, but we were able to get away with most of it, but there were some portions of the code where without refactoring we couldn't get away at all. So,
and I guess the summary too is you're trying to minimize refactoring in order to
yes.
preserve the original scientific code.
Yes.
Just insert directives where you can.
Yes, that is correct. Because the scientists are very particular about readability. They want to be able to look at the code and say which equation this code kind of trying to solve. So as such, yes, we tried to maintain as much as we could.
Okay, thanks.
I think Dr. Freitas had his. Oh, okay.
Yes, thank you. Concerning the sharing the code with any car, you mentioned that you have the version 6.3 that is in
yes.
the control system of any car, right? And they
yes.
are now in 7.0.
Well, 7.0, but there is also, if you look at the master branch is 7.0, but if you look internally, there's also a 7.3.
Okay.
So the latest version is 7.3, and the September release of MPass on GPUs would be 7.3. It would be basically the latest branch.
Okay, that will incorporate the change that you showed today, right?
Yes, the change is basically we have submitted the pull request on the GitHub, so it's going to take them a couple of months by the time they actually approve and accept it. Yes, but you should have that by end of September.
Okay, and you plan to keep this collaboration very closely with NCAR because, as you know, they are going to develop model further, right?
So we are working with actually making them completely independent. So there are two perspectives here. One is we have the weather company that we support, which looks like they're going to be using MPass on GPUs for a long time, similar to your plans. So we're trying to support them. And at the same time, we are trying to also make NCAR and TWC independent. So we have been successful in getting both the weather company as well as NCAR to hire GPU developers. So that every time there is a code upgrade, the code release would basically be for both GPU and CPU. So that way it would be less what you call as a dependency on NVIDIA. But yes, our intention is to support with NCAR and TWC as long as possible, as long as they want us. But I think they're also becoming independent. They have a separate department of GPU developers, including TWC has also hired GPU developers so that they can basically update this on their own and then keep the repository up to date. So you see the effort from both the sides, not just one.
And I'll add that having a relationship with NCAR, same as NASA Goddard, is fundamental to our program.
Yes.
It will always exist.
Okay, that's great.
Our collaboration with NCAR is not limited to MPass. We are also collaborating on climate projects like Earthworks, which is basically climate models. So it's a long-term 5-year plan. So there's no near future where we are out of the relationship. But our relationship with NCAR is very fundamental, so it's going to be there for a long time.
Okay, well, and CSM where there's opportunity.
Yes.
MPass will later be an atmosphere option for the component in CSM. So that'll continue.
Yes.
Okay, thank you.
So, yeah.
No. Go ahead.
Is there any other question or? Otherwise, I just want to show how this changes. I think. Sorry. I just wanted to show how the time step changes or how you can basically calculate I had a simple table that I was basically able to do. Give me just 1 minute, I can pull it up. This was for the 10-kilometer resolution. You were asking on how to basically calculate how the timing works. Let me pull that up really quick. I can probably share with you if nobody else has any questions, that is.
I guess you can go ahead.
Okay, give me just a minute, I'll pull this up.
Okay.
How do I share? Yeah, here it is. Perfect. So this is basically kind of a template. I'll walk you through by it. So on the left side, you can see data sets, which is 120 kilometer, 60 kilometer, 30 kilometers, and the total number of grid points. And I do have some noise. I'm not sure from where. I can hear a lot of noise that's coming back. Oh, perfect. Thank you. I don't know. Am I the only one hearing a lot of noise, sir?
Let me see. We can hear you.
Okay, then I'll keep going. So you can see here what we're doing is kind of figuring out how much of the cost effectiveness versus performance. So on the time per time step side, you can see that what we're doing is for every given resolution, we are taking one GPU, but we are basically having more ranks per GPU work on it, fixed number of radiation ranks, and the number of grid points per GPU is being changing. So on the finer side, if you look at it, you have a very, very low time per time step. So, and this is something you can probably go with where you have a faster performance, 0.29 seconds, and you can generate all the way up to 0.14 years per day. And then the estimated time to complete a 72-hour forecast would be basically just 1.63 hours. That would be your best time. But this is where you're going for a fast performance model. But if you're basically going for the other side of the spectrum, here you can see 1.95 time per time step is what we have. But you have 655,000 grid points per GPU. And you can get the best here is about 9.72 hours in order to do a 72-hour forecast. However, you're doing all of this on just a single GPU. So based on what your requirements are, so if you give me saying, look, we are looking at a 10-kilometer resolution and we're planning to run it for four times a day or 8 times a day, and this is our kind of constraints, then I can probably go back and then provide you with options like these, saying, okay, look, if you are budget constrained, then this is the minimum number of GPUs. But if you're performance constrained, this is the number of GPUs that you would require to run the MPAS. So I can do that studies for you and get back to you once I have a detail about the grid and the constraints that you have.
Oh, that's great. We are planning to have 10-kilometer global uniform resolution. Mm-hmm. And we expect to have a 10 days forecast, less than 2 hours production time, right?
I see. Okay. So
what would be how powerful the system should be to in 2 hours provide 10 days forecast with 10 kilometers and 72 levels, vertical levels. You can start the same number of levels that you have in this study you have.
Got it. So for this, that basically means you really want to run at about less than this. So basically, you want to have only about 20,000. So you can see here, this column here has the grid points per GPU. So that one, basically, you want to run finer than 40,000. So I'm assuming at about 10,000 grid points per GPU is what you really want to run. That would give you about 3x performance boost. Yes, that is correct. I think I can make the table and send it back to you. In the grid points per GPU, if you can run about 10,000 points per GPU, then the timing here would be sufficient enough where you get about 1/3 of this number, 1/3 of 1.63. So that would be basically for 72-hour forecast. So if you triple that, that would be basically a 10-day forecast. So the 10-kilometer grid, if I remember correctly, is how much? 5.6 million points, right?
I'm not sure.
I think, yeah, the 10-kilometer resolution is 5.6 million points. So if you have that, 560 GPUs, you would be able to get the 10-day forecast in 2 hours, approximately. I can actually run the simulation for you and get back to you, but yeah.
Oh, that's great. That would be great, yeah.
So for impasse, that's non-hydrostatic, but do you all plan to use hydrostatic at 10 kilometer? Or does impasse have an option for hydrostatic?
Not that I know of. I don't think impasse has an option for hydrostatic.
Yeah, I don't know yet also if they have some switch that it can turn off the non-hydrostatic part, yeah. I think they run no hydrostatic like Worthy. For any resolution, they just have the same dynamics.
Yeah, so if you're really interested, I can run the simulation, get an estimate for you, but I think 70 nodes is what you're looking at with 8 GPUs each.
Well, it will be very, very useful for us to determine which dynamic core you are going to use if you have these numbers, practical numbers that reflect that what you are planning to run in the next year.
Perfect. So what I'll do is I'll go back and then run some simulations for you and provide you these estimates. I will also provide you a strong scaling curve for a 10-kilometer resolution, since it's of interest to you. So that way you can extrapolate in any direction and see what would be the best fit for you.
Okay. Yeah.
And do you plan an ensemble prediction system? And if so, what resolution for each member and how many members, please?
Well, we did not decide yet very carefully about the ensemble, but we think you should go to 30 kilometers, maybe 24 to 36 members. But we still need to talk about. So we are focused now on the deterministic prediction only.
Okay, thank you.
Now maybe Carlos Bastard can say a few words about that.
Hi, Saulo. I agree with you. I think the first part that we have to set is the deterministic part of the problem. And then we can talk about the ensembles. But my question previously was if the GPU can make a difference in the sense. But as was said, the answer was that there's no easy fix, right? So we have to deal with that, and maybe data simulation can help, because as far as I can say, the use of the GPUs and the ensemble problem is mostly related to the machine learning problem, and not exactly the optimization of the code while running in an ensemble sense, and the use of the GPU. So that's basically it.
Okay, and I mentioned I'll send out some details. So we have two cases. There was a machine learning implementation by ECMWF on the data assimilation, the 4D bar. I'll send that. But also the Medio Swiss actually ported their data assimilation code to the GPU for their operational system. So we have examples of both, and I'll provide those to Fernando.
Okay.
If I may ask, what's the timeline for your decision-making process between selecting between the FV3 and MPAS?
Will be about 1 year from now.
Perfect. Okay.
Yeah.
So basically, that means I can wait till the 7.3 release and then provide you with. I'm just trying to see when is the best time to provide you a 10 kilometer curve that will help you with the number of GPUs. So is it okay if you wait till the October, or is that something that you want to ponder over before that?
No, that's okay. October will be fine. Yeah.
Perfect.
As soon as possible. Yeah.
Okay. Any other questions? So, if we will not have another questions, we can close this session today. Next Wednesday, we will have another session with Dr. Oliver Führer that will be talking about GPU development of FV3. Correct, Stan?
Yes, that's correct.
Okay, that's great. I will be sharing this recording with you guys, okay, as soon as I save this. And thank you very much for the audience.
Yeah,
Okay, thank you. I just want to say, apologize by Professor Pedro Diaz and Luis Flavio. They got last minute issue. They do not come, but they are going to watch the record.
Okay. Thank you very much.
Professor Diaz.
Thank you
so much.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Thank you very much. Yep. Bye.